Welcome to another deep dive, and this time we're tackling something that's literally holding our world together.
Hmm, sounds intriguing.
Oh, it is. We're going to be looking at the design of main beams and how they support all those secondary beams you find in any structure.
Ah, the unsung heroes of the construction world.
Exactly. And we're basing this deep dive on a fascinating article called Understanding the Design of Main Beams Supporting Secondary Beams in Construction. It's packed with insights, and trust me, you'll never look at a beam the same way again.
I'm ready to have my perspective on beams completely transformed.
So to kick things off, let's start with the basics. What exactly are main beams and secondary beams?
Well, you can think of it like a human skeleton. The main beams are like the spine.
The primary load-carrying element.
Exactly. They transfer the weight of the entire structure down to the foundation. Then you have the secondary beams, sometimes called joists.
And those would be like the ribs.
Yes. Branching out from the spine. They distribute the load more evenly.
Ah, so it's all about teamwork. The main beams are doing the heavy lifting, and the secondary beams are helping to spread the weight around.
Precisely. And that distribution is crucial because it prevents any one point from becoming overloaded. It's a brilliant example of how engineering principles mimic nature's efficiency.
The article really dives deep into the world of reinforcement, and that's where things start to get really interesting. It talks about these things called hanger bars. What exactly are those?
Ah, yes, hanger bars. These are steel bars that are strategically placed at the junction, where a secondary beam meets a main beam.
Yeah.
And they act like clamps, preventing the secondary beam from twisting or pulling away from the main beam when it's under stress.
So they're essentially keeping that connection strong and stable.
Exactly. And here's the thing, the placement of these bars is incredibly precise. The article says they're positioned at 1.5p.
1.5p, what does that mean?
Haze represents the depth of the main beam.
Ah, okay.
It really shows the level of detail and precision that goes into structural engineering.
It's fascinating. And speaking of precision, the article also mentions close rings. What can you tell us about those?
Close rings, sometimes called stirrups, are basically like little hoops of steel.
Hoops of steel. Interesting.
Yeah, and they wrap around the beams, especially near the junctions. You see, they help to resist shear forces.
Shear forces. Could you elaborate on that for our listeners who may not be familiar?
Imagine you're trying to cut a loaf of bread with a dull knife.
Okay, I'm visualizing that.
The force you're applying is like shear force trying to slice through the beam diagonally. Close rings prevent this by holding the concrete together, distributing those forces more evenly.
Ah, I see. So hanger bars prevent twisting, and closed rings prevent the beam from being sliced apart. Are there any other important reinforcement components?
Oh, there are a few more. We have shear links.
Similar to stirrups.
Yes, quite similar. They also resist those pesky shear forces, but are especially important in beams that have the same depth, providing extra strength at the connection points.
Interesting. So different reinforcements for different scenarios.
Exactly. Then we have suspender stirrups.
And what do those do?
These are crucial when you have beams of unequal depths.
Unequal depths. So one beam is taller than the other.
That's it. And this difference in height can create extra stress at the junction.
I can see how that would be a problem.
Exactly. So suspender stirrups act like anchors, securing the secondary beam into the main beam, preventing instability. A truly ingenious solution, I might add.
It's amazing how these different reinforcements work together, each with its own specific job to do.
It's all about teamwork.
But I imagine the placement of these bars is critical too, right? You can't just stick them anywhere.
Absolutely. The location of each reinforcement bar is meticulously calculated. It needs to provide the right support in the right place.
Makes sense. So for example, where would you typically find the main reinforcement bars?
Usually, you'll find them at the bottom of the main beam. You see, they carry most of the tensile load.
Tensile load. Now remind me what that is again.
Basically, tensile load is the force that tries to stretch the beam. Picture pulling on a rubber band, that's tension.
Okay, that makes sense.
The main reinforcement bars are specifically designed to resist this stretching, preventing the beam from sagging under pressure.
So it's all about placing the right type of reinforcement in the right spot to counteract the forces acting on the beam.
You got it. It's like a complex puzzle of forces and counterforces, and structural engineers, they have to carefully analyze it all to create a stable and safe structure.
I'm realizing there's a lot more to beams than meets the eye. It's truly fascinating, but it makes me wonder, how do engineers know how much reinforcement a beam actually needs? Is there a formula, or is it just based on experience?
Oh, it's definitely not a guessing game. There's a whole science behind calculating the amount of reinforcement. They take into account factors like the types of loads, the span length, and the materials being used.
Sounds complex.
They can be, but thankfully, engineers have developed formulas and software programs to help them with these calculations.
That's reassuring. So a lot of responsibility rests on the shoulders of these structural engineers.
Absolutely. Their work is fundamental. They literally keep our buildings standing. Precision and accuracy are paramount in their field.
So before we delve further, let's just quickly recap what we've covered so far. We've talked about the roles of main and secondary beams, how they work together to distribute weight, and the different types of reinforcements used to keep them strong.
And we've touched on those all-important calculations that engineers use to determine the precise amount of reinforcement needed for each beam. It's a lot to take in.
It is. But hopefully it's giving everyone a clearer picture of this hidden world inside the structures we see every day.
Absolutely. It's a world of incredible complexity and precision.
And I'm curious to learn how these principles apply to different types of buildings. I mean, a skyscraper is quite different from a small house, right?
That's a great point. And yes, the design considerations change depending on the type of structure.
So for example, would a skyscraper have different design considerations compared to a bridge?
You bet. We've only just scratched the surface of the world of beams and the incredible engineering behind them. There's so much more to explore.
Absolutely. A skyscraper and a bridge, they face completely different challenges, and that's reflected in their beam designs. Let's start with skyscrapers. One of the biggest factors is their height.
Makes sense. They are all about reaching for the sky. So how does that affect their beam design?
Well, imagine stacking thousands of bricks, one on top of the other. That's the kind of pressure we're talking about.
Wow, that's a lot of pressure.
It is. Skyscrapers have to handle these massive compressive forces pushing down on the beams from all those floors above.
So the beams need to be incredibly strong to withstand all that weight.
Exactly.
Yeah.
And not just strong, they also have to be stiff enough to prevent too much swaying.
Right. You wouldn't want a skyscraper that sways too much in the wind.
Exactly. That's why skyscraper beams are often made of high-strength steel or concrete.
And of course, they're reinforced.
Yes, with a very complex network of steel bars, similar to what we discussed earlier. It's amazing to think about all those forces silently at work, keeping these massive buildings upright. But I imagine wind also plays a significant role, especially at those heights.
Oh, absolutely. Wind can create some incredibly powerful horizontal forces, especially on tall, slender structures like skyscrapers.
So it's not just about preventing the building from collapsing downwards, but also from being pushed sideways by the wind.
Exactly. And that's where things like diagonal bracing and shear walls come in.
Ah, working together with the beams.
Precisely. They all work together to create a super rigid structure that can withstand both the vertical and horizontal forces.
So it's a real team effort to keep a skyscraper standing strong.
A real team effort. Designing a skyscraper is like a giant puzzle. Engineers have to carefully consider all these different forces and elements to create a safe and efficient structure.
Okay, so we've talked about the challenges of building upwards. What about bridges? Those structures that stretch horizontally across vast distances. How do their beam designs differ?
Well, bridges have their own unique set of challenges. One of the main ones is the constant change in loads due to traffic.
So unlike a skyscraper where the weight is relatively constant, a bridge has to deal with cars and trucks constantly moving across it, creating dynamic loads.
Exactly. And the weight can fluctuate dramatically depending on the type and volume of traffic.
Right. A fully loaded truck exerts a much greater force on a bridge than a small car.
Exactly. So the beams have to be designed to handle those constant changes in weight and also the vibrations that come with all that traffic.
I remember from physics class that longer beams tend to deflect more under load. So I imagine the length of a bridge plays a significant role in the beam design.
Absolutely. The longer the span of a bridge, the greater the deflection under load. Bridge engineers use sophisticated calculations and computer models to figure out the optimal shape, size, and reinforcement for the beams.
Ensuring they can safely accommodate those deflections. So it sounds like both skyscrapers and bridges require careful consideration of the loads they'll experience, but the specific design solutions are going to differ based on the structure's purpose and the forces it needs to withstand.
That's a great summary. It's a testament to the ingenuity of engineers that they can design structures that seem to defy gravity, whether they are reaching for the sky or spanning vast distances.
It makes you appreciate the hidden complexity in something as seemingly simple as a beam. But thinking about all these different structures, are there any universal principles that apply to beam design, regardless of the structure?
That's a great question. And yes, despite all the variety, there are some fundamental principles that underpin all beam design. One of the most important is understanding and managing the forces that act on a beam. We're talking about tension, compression, and shear.
We touched on those courses before, but could you give us a quick recap?
Absolutely. Imagine a beam supported at each end with a weight in the middle. The top of the beam is being compressed or pushed together, while the bottom is under tension being pulled apart.
So it's being squeezed on the top and stretched on the bottom.
Exactly. And then you have those shear forces trying to slice through the beam, like we talked about earlier. Engineers need to carefully consider all of these forces and design the beam and its reinforcement to resist them effectively.
So regardless of whether it's a skyscraper, a bridge, or even a small house, understanding and managing these forces is fundamental to beam design.
Absolutely. It's the foundation. And that's what makes beam design so fascinating. It's this interplay of forces, materials, and human ingenuity that allows us to create all of these incredible structures we see around us.
It really is amazing to think about the thought and engineering that goes into something as seemingly simple as a beam. But speaking of engineering, I'm curious to know more about the actual construction process. How are these massive beams put into place, especially in tall buildings or along bridges?
That's another fascinating aspect of structural engineering. You see, the methods used to erect those beams depend on a number of factors, like the size and weight of the beams, the height of the structure, and the accessibility of the site.
So there's no one-size-fits-all approach.
Not at all. Sometimes they use cranes to lift the beams into place, especially for those larger beams and taller structures. And in other cases, they use special hydraulic jacks to slowly and carefully raise the beams from the ground.
I imagine it's quite a sight to see these massive beams being lifted and maneuvered into place.
Yeah.
It must require a high level of precision and coordination.
Oh, absolutely. It's a delicate dance of engineering and construction, with teams of skilled professionals working together to ensure that the beams are installed correctly and safely.
It's a real testament to human ingenuity that we can build such incredible structures, from those towering skyscrapers to the sprawling bridges. But I'm also curious about the future of beam design. What innovations and advancements are on the horizon?
Well, the world of structural engineering is always evolving. There are some exciting developments when it comes to beam design. One area that's generating a lot of buzz is the use of new materials.
Yeah, the article mentioned high-performance concrete and fiber-reinforced polymers. What are those all about?
Well, high-performance concrete is basically, as the name suggests, a much stronger and more durable version of traditional concrete. It can withstand higher loads, and it's much more resistant to things like cracking and weathering.
So it would be a great choice for structures that need to withstand some pretty harsh conditions
Exactly.
or heavy use.
Right. And then we have fiber-reinforced polymers, or FRPs for short.
FRPs, okay.
These are incredibly strong and lightweight materials. They're made by combining fibers like glass or carbon with a polymer matrix.
Interesting. So what's the advantage of using FRPs?
Well, they offer an impressive strength-to-weight ratio, so they are ideal for applications where weight is a major concern.
Yeah, bridges.
Exactly. Or aircraft.
It sounds like FRPs could be a real game changer.
Yeah.
But what about the environmental impact? Are they more sustainable than traditional concrete and steel?
That's a key consideration, and researchers are definitely working on developing and refining these materials to minimize their environmental footprint.
So there's a lot of research going on in that area.
Yeah. For example, some FRPs can be made using recycled materials, and there are advancements in manufacturing processes that are reducing the energy required to produce them.
That's encouraging. It seems like sustainability is becoming a top priority in structural engineering these days.
Oh, absolutely. And it's not just about the materials themselves. We're also seeing a shift towards more sustainable design practices overall.
In what way?
Well, like optimizing beam shapes and sizes to use less material,
Yeah.
or incorporating things like passive design principles to reduce energy consumption in buildings.
It's great to see how the field is evolving to meet these challenges. But with all these exciting new materials and techniques, I'm wondering about the role of those traditional reinforcement methods we discussed earlier, like hanger bars and stirrups. Are they becoming obsolete?
That's a great question. While new materials offer exciting possibilities, those fundamental principles of reinforcement are still very much relevant.
So the basic principles haven't changed.
Right. We might find more efficient ways to achieve the same structural goals, but the underlying need to resist forces like tension, compression, and shear, those are always going to be there.
So it's not about replacing the old with the new.
It's about integration.
Yeah, finding ways to integrate the best of both worlds.
Exactly. We can leverage the strengths of new materials and technologies while also building upon the knowledge and experience gained from decades of traditional structural engineering.
The article briefly mentioned 3D printing. It seems like that could really revolutionize how we build with beams in the future.
Oh, absolutely. 3D printing is already being used to create really complex beam shapes and designs that would have been impossible or at least prohibitively expensive to produce using traditional methods.
So it's opening up a whole new world of possibilities.
It really is. And as the technology continues to advance, we can expect to see even more innovative applications. It has the potential to significantly reduce construction time, waste, and costs.
And it allows for much more design freedom. It's incredible to think about the possibilities. But with all these advancements, do you ever worry about losing sight of the human element in construction? The skill and craftsmanship that go into building these structures?
That's an important consideration. We need to be mindful of that as technology advances. The human element will always be crucial in construction.
So it's about finding the right balance.
Exactly. Finding the right balance between leveraging technology to improve efficiency and safety, while also valuing and preserving the artistry and expertise of skilled craftspeople.
It's a good reminder that behind all the calculations, materials, and technology, it's people who bring these structures to life.
Absolutely. It's a real testament to human ingenuity and collaboration.
Well, this has been a fascinating deep dive into the world of beams. We've learned so much about their design, their importance in different structures, and all the exciting advancements that are on the horizon.
It really has been.
I think I can safely say we both have a newfound appreciation for beams.
The unsung heroes of the built environment.
Exactly. Thank you so much for joining us on this deep dive into the world of beams. And the next time you walk into a building or cross a bridge, take a moment to appreciate those beams, the incredible engineering, and the silent strength that are holding it all together. Until next time.